Okay, so you've really gotten into organic chemistry, haven't you?
Yeah.
You've sent over a ton of notes and textbook pages, and it's all aldehydes, ketones, and carboxylic acids.
Looks like someone is becoming a carbonyl compound connoisseur.
We're going to break down all of these organic compounds today, their names, structures, how to make them, and even some of their sensory properties.
It's really like opening a door to a whole new world, these carbonyl compounds. They're the backbone of so many things we see and use and smell every single day, from the scent of cinnamon and vanilla to the materials in our clothing and even the medicines that we rely on.
So we're talking about aldehydes, ketones, and carboxylic acids. Um, they're all connected by this carbonyl group, right? But what makes each one different from the others?
You've hit the nail on the head. That carbonyl group is definitely the common thread, a carbon atom double bonded to an oxygen atom. But it's the atoms surrounding that carbonyl group that really gives each compound its unique personality. Think of it this way. Imagine a really busy city square. The carbonyl group is that central fountain, but depending on the shops and the buildings that are surrounding it, you get a different vibe. So you might get a bakery, a clothing boutique, or maybe even a pharmacy.
I love that analogy.
Air.
So aldehydes, ketones, and carboxylic acids each have their own kind of molecular neighborhood that defines their character. But before we get into their individual personalities, let's talk about naming conventions. I always think it's so fascinating how chemists come up with these names. They're so quirky sometimes.
It's like a secret language, right?
Yeah.
So we have these common names. The common names often reflect the compound's history or where it came from. For example, formic acid was named after ants, because that's where it was found, in their venom. And then we have the more systematic IUPAC system, and that system makes sure that everyone is speaking the same chemical language.
So common names are like nicknames, and IUPAC names are their official titles.
Exactly.
Speaking of titles, let's give aldehydes and ketones their spotlight first. How do their names and structures actually differ?
All right, so picture that carbonyl group in your mind, that central carbon atom that's double bonded to the oxygen. Now, in an aldehyde, one of the carbon's other bonds is always going to be to a hydrogen atom. It's like that carbonyl group is standing at the edge of the dance floor, just holding hands with hydrogen.
Okay, so aldehydes always have that hydrogen partner. What about ketones? Do they get to dance with somebody too?
Ketones are more outgoing. Instead of hydrogen, ketones have two carbon-containing groups that are attached to that carbonyl carbon. So they're always mingling with other carbon groups.
Also, they're the life of the party.
Exactly. And their IUPAC names really reflect that. They usually end in one, like propanone. That's the simplest ketone.
So for aldehydes, like formaldehyde and 1,1. For ketones, like acetone, that familiar nail polish remover scent. But names are just the beginning. Let's get to the heart of the matter, their molecular structures. What secrets does that carbonyl group hold that makes these compounds so special?
It's all about those electrons. The oxygen in that carbonyl group is a bit of an electron hog. It pulls electron density away from the carbon, and that creates a slightly positive charge on the carbon and a slightly negative charge on the oxygen.
Ah, so we've got this push and pull happening within that carbonyl group, creating a polar bond. Does that make it reactive?
Exactly. That partially positive carbon is like a beacon for electron-rich species, the ones called nucleophiles.
Right.
And those nucleophiles, they're always looking to share their electrons, and this attraction is what leads to nucleophilic addition reactions.
So the carbonyl group structure really sets the stage for all these fascinating interactions. It's like a molecular magnet attracting those nucleophiles to come and play.
Huh.
But before we dive into all the reactions, you mentioned resonance. What role does resonance play in the story of the carbonyl group?
Okay, so resonance is a way to describe how electrons can spread out or delocalize within a molecule. In that carbonyl group, the electrons that are in the double bond, they're not fixed. They can shift, and they can create a temporary situation where that carbon has a full positive charge and the oxygen has a full negative charge. It's like a seesaw. Those electrons are constantly redistributing to create this dynamic balance.
So it's not a static picture. Those electrons are always on the move. Does this electron dance have any real consequences for the carbonyl group?
Absolutely. That resonance stabilization makes the carbonyl group even more reactive. So it's like that carbon is constantly sending out signals saying, hey, nucleophiles, come over here.
Wow.
And it's this increased reactivity that makes carbonyl compounds so fascinating and versatile.
Okay, this is starting to click. So we have these carbonyl compounds with these unique structures and this intriguing electron dance that makes them highly reactive. But how do we actually make these aldehydes and ketones in the first place? Do they just appear out of thin air?
Not quite. Chemists have actually developed some very clever ways to synthesize these compounds. Think of it like a molecular cooking show. We have all these different recipes and techniques depending on what we want to create. So, for example, if you want to oxidize an alcohol, that's like gently simmering it with an oxidizing agent to transform it into either an aldehyde or a ketone.
So we're using these oxidizing agents to just tweak the molecular structure. We're transforming alcohols into aldehydes or ketones.
Yeah.
Amazing how chemists can control all of these molecular transformations.
And there are other techniques too. We can actually remove hydrogen from alcohols using a catalyst. And that process is called dehydrogenation. It's like carefully extracting a specific ingredient to create a new flavor profile.
It's like having a molecular toolkit and choosing the right tool for the job. So we've got oxidation, we've got dehydrogenation. What other techniques do chemists have up their sleeves? I've always been so intrigued by ozonolysis. It sounds like something straight out of a sci-fi movie.
Ozonolysis is a really powerful technique. It's like using a molecular laser to split an alkene. So that's a compound with a carbon double bond.
Right.
And then adding oxygen to those cleaved ends, which forms aldehydes and ketones.
Wow. So we're using ozone to essentially break that molecule apart and then adding oxygen to create these new compounds. That's incredible. But how do we control whether we get an aldehyde or a ketone? Is it a matter of precision or just molecular luck?
Precision is key. It all comes down to the location of that double bond in the starting alkene. If that double bond is at the end of the carbon chain, kind of like a flagpole on top of a building, you're going to end up with an aldehyde. But if it's located somewhere in the middle, like a doorway on a busy street, you're going to get a ketone.
It's like a molecular treasure hunt. We've got our alkene, we use ozone to split it open, and then depending on where that split happens, we find either an aldehyde or a ketone waiting for us. This is all so fascinating.
And that's just the beginning. There's a whole world of specific techniques for preparing aldehydes and ketones. And each technique comes with its own set of steps and conditions. It's really like a culinary adventure, experimenting with all these ingredients and techniques to create the perfect molecular dish.
I can't wait to explore those specific techniques. But before we dive into that recipe book, let's talk a little bit about the sensory properties of aldehydes and ketones. I know they're responsible for so many familiar scents and flavors. What makes them so special in the realm of our senses?
Think about the smell of cinnamon or vanilla, those warm, inviting aromas. Well, those are thanks to aldehydes and ketones. Their molecular structure, especially that specific arrangement of the carbon and oxygen atoms, interact with the receptors in our noses, and that triggers those scent sensations.
So it's like a molecular dance between these compounds and our olfactory receptors. And their size and shape all play a crucial role in determining that specific scent. But what about flavors? Do aldehydes and ketones contribute to our taste buds as well?
Absolutely. Many fruits and spices owe their characteristic flavors to aldehydes and ketones. Benzaldehyde gives almonds their distinctive bitter taste. And then we have that sweet, creamy flavor of vanilla that comes from vanillin. And that's an aldehyde. It's like nature's own flavor laboratory.
It's incredible how these seemingly simple molecules can create such a diverse range of sensory experiences.
Right.
We've gone from understanding their structure to how they affect the taste of our food and even the fragrance of our perfumes. It really highlights how chemistry is intertwined with our everyday lives. But now I'm ready to put on my chef's hat and dive into those specific techniques for preparing aldehydes and ketones. Let's unlock the secrets of these molecular recipes.
All right, let's start with aldehydes. One method that really stands out is Rosenman reduction. Imagine taking a reactive acyl chloride. So that's a molecule with a chlorine atom attached to the carbonyl group. And we're going to gently tame it with hydrogen gas and a palladium catalyst.
Acyl chloride, that sounds intense. It sounds like a wild ingredient that needs to be handled carefully.
You could say that they are quite reactive, but the Rosenman reduction actually allows us to transform them into the milder mannered aldehydes. It's like taking a fiery chili pepper and turning it into a sweet bell pepper.
That's a great analogy. So we're using this specific technique to control the reactivity and create a product that's a little bit more desirable. And what about the other methods for preparing aldehydes? I see we have reduction of nitriles and esters, as well as some specific recipes for those elegant aromatic aldehydes.
Okay, so nitriles with their carbon-nitrogen triple bonds, those can be coaxed into becoming aldehydes. We use reducing agents and a bit of hydrolysis, a process where we break bonds using water. It's like carefully separating the layers of a complex pastry to create something new and delicious.
So we're using these reducing agents to strategically break and reform bonds, transforming those nitriles into aldehydes. And what about esters? Can they be transformed into aldehydes too?
Esters are like molecular chameleons. They can be reduced to aldehydes using very similar techniques. For example, specific hydride reagents that act like tiny delivery trucks, bringing hydrogen atoms to exactly the right location.
It's amazing how chemists have figured out all of these intricate molecular transformations. And what about those aromatic aldehydes with their elegant ring structures? Do they have their own special recipes?
They do. One common approach is to take an aromatic hydrocarbon, like toluene, and you selectively oxidize it using reagents like chromal chloride. It's like carefully polishing a rough gemstone to reveal its brilliance.
So we're targeting a specific part of the molecule and transforming it into an aldehyde. And this is specifically for aromatic compounds.
Exactly. These methods are particularly effective for creating benzaldehyde and its derivatives, which are molecules that often contribute to those enchanting floral scents.
This is all so fascinating. We've explored a whole range of methods for preparing aldehydes, from taming those reactive acyl chlorides to selectively oxidizing aromatic hydrocarbons. It's like a molecular symphony, with each technique playing its unique part. But now I'm curious about ketones. Do they have their own set of preparation methods, or do they share some secrets with aldehydes?
Ketones have some tricks of their own up their sleeve. One interesting method involves reacting the acyl chlorides again, but this time with these special organometallic reagents called dialkyl-cadmium reagents. It's like a molecular tango, carefully choreographing the interaction between those two partners to create that ketone.
So we're taking acyl chloride, swapping out chlorine, and then introducing alkyl groups from that cadmium region.
You got it. It's like a molecular swap meet, trading one part for another to create a new and interesting molecule.
I love these analogies. And we can also make ketones from nitriles using Grignard reagents, right? Those versatile organometallic compounds that are always ready to add carbon groups to other molecules.
Absolutely. Grignard reagents are like molecular construction workers always ready to build and expand. Reacting them with nitriles followed by a touch of hydrolysis is a very reliable way to create ketones.
So we're using Grignard reagents to build up our ketone structures.
Yeah.
And I remember Friedel-Crafts acylation from organic chemistry class. That's another classic reaction for adding carbonyl functionality.
Yeah, you have a sharp memory. Friedel-Crafts acylation is a powerful tool for attaching acyl groups to aromatic rings, which creates those aromatic ketones. It's like adding a decorative touch to a beautifully crafted molecule.
This is all so incredible. We've covered so much ground, from the basics of aldehydes and ketones to specific techniques for preparing them. But I'm ready to shift gears a bit. Let's delve into the world of their physical properties. What can we tell about these compounds just by looking at them, smelling them, or even feeling them?
That's a great question. Their physical properties are directly linked to their molecular structures and the forces that exist between those molecules. Think of it like a group of people at a party. How they interact with each other really depends on their personalities and how they attract or repel one another.
I love that analogy. So how do these molecular personalities affect properties like boiling point? How do aldehydes and ketones compare to other organic compounds like hydrocarbons or alcohols?
Well, aldehydes and ketones have that polar carbonyl group, right?
Yeah.
So those dipole interactions between molecules, the attractions between those slightly positive and negative charges, makes them stick together more tightly than nonpolar hydrocarbons, which don't have that charge separation.
Yeah.
And this means they have higher boiling points.
So those dipole interactions from the carbonyl group make them more attractive than hydrocarbons. But what about alcohols? They have that strong hydrogen bonding, right? How do aldehydes and ketones measure up against those?
Alcohols are like the social butterflies of the molecular world. They can form those strong hydrogen bonds with each other. Aldehydes and ketones, while polar, they can't quite match that level of bonding, so their boiling points are usually lower than alcohols of a similar size.
Interesting. So aldehydes and ketones fall somewhere in between hydrocarbons and alcohols when it comes to boiling point. Their polarity makes them more attractive than hydrocarbons, but they lack the strong social skills of alcohols.
Exactly. And this balance of intermolecular forces also affects their solubility. Smaller aldehydes and ketones, the ones with shorter carbon chains, are soluble in water because they can form hydrogen bonds with water molecules. But as the size of those hydrophobic carbon chains increases, they become less willing to mingle with the water molecules.
Ah, that classic hydrophobic-hydrophilic struggle. The water-loving carbonyl group is trying to fit in, but those larger water-fearing hydrocarbon chains, they want to stay away from the party.
Exactly, and this interplay between polarity and molecular size also influences their odor. Smaller aldehydes often have very sharp, pungent odors, while larger aldehydes and ketones tend to have more pleasant, even floral or fruity aromas.
Wait, so that's why some perfumes smell so good.
Yes.
It's because of those larger aldehydes and ketones. Amazing how something as simple as a carbonyl group can lead to such a variety of scents.
It is pretty incredible.
But speaking of sensory experiences, what about taste? Do aldehydes and ketones contribute to flavors as well?
Absolutely. They're nature's flavor artists. Many aldehydes and ketones are responsible for the characteristic flavors that we taste in fruits and spices. Benzaldehyde, that gives almonds that bitter taste.
Right.
And then there's vanillin, which contributes to that sweet, warm flavor of vanilla.
It's incredible how these compounds can influence so many different aspects of our sensory experiences. We've gone from understanding their structure to learning how they affect the taste of our food, the fragrance of perfumes. It really highlights how chemistry is intertwined with our everyday lives. But now I'm ready to switch gears and delve into the world of their chemical reactions. We know that they're reactive because of that polar carbonyl group, but what kind of reactions are we talking about?
One of the most important reactions is nucleophilic addition. Remember those nucleophiles, those electron-rich species that are attracted to that partially positive carbon in the carbonyl group?
Right.
Well, they don't just admire it from afar, they attack and they add themselves to the molecule.
Okay, so we've got these nucleophiles, like tiny little molecular missiles drawn to that vulnerable carbon in the carbonyl group, and they add themselves to the molecule, creating something new. But how does that actually happen? What's the mechanism behind this nucleophilic addition?
Imagine the nucleophile approaching that carbonyl carbon. It's like a dancer gracefully moving towards their partner. This approach actually breaks the pi bond of the carbonyl group and pushes those shared electrons onto that oxygen atom.
So the double bond opens up, and the nucleophile gets to join the dance. What happens next?
The carbon atom, which is now bonded to that nucleophile, it changes its shape. It forms what's called a tetrahedral intermediate. It's like a quick change of partners in that molecular dance.
Okay.
This intermediate is usually unstable, and it'll quickly grab a proton from its surroundings to stabilize itself.
So it's like this carefully choreographed molecular ballet. The nucleophile attacks, the double bond breaks, a new bond forms, and then a proton comes in to stabilize everything. It's pretty amazing.
Yeah.
But how do we know which nucleophiles will actually react with aldehydes and ketones? Are they all equally eager to join the dance floor?
Not all nucleophiles are created equal. Their reactivity really depends on a few factors, things like how rich they are in electrons, their size, and even the overall reaction conditions. It's like a molecular matchmaking service. We need to consider compatibility and make sure we have the right environment for a successful reaction.
So some nucleophiles are more eager to react than others.
Yeah.
But what about steric hindrance? Does the size of the nucleophile actually matter? It's like trying to fit a large dancer onto a really crowded dance floor.
You're exactly right. If the carbonyl group is surrounded by large, bulky groups, it can make it really...
Got it. So it's not just about willingness, it's also about finding the right fit. The nucleophile needs to be enthusiastic and agile to join that molecular dance floor. But now I'm curious to see some specific moves. What are some common examples of nucleophilic addition reactions that aldehydes and ketones will undergo?
One classic move is the addition of hydrogen cyanide, HCN, and that forms what we call cyanohydrins.
Okay.
That's like adding a special ingredient, that cyanide group, to the molecule. This reaction is incredibly useful because it extends the carbon chain and it introduces a new functional group. And that really opens up a ton of possibilities for creating a wide variety of other compounds.
So it's not just about that initial step, it's about the possibilities that unfold afterward, like a domino effect. What about other nucleophilic additions? What other moves can we perform on these molecular dance floors?
Another interesting reaction is adding sodium hydrogen sulfite, and that's NaHSO3. It's like attaching a little temporary tag to an aldehyde. It makes it water-soluble, and it allows us to separate and purify the aldehydes from other compounds. So it's like separating dancers that are wearing specific costumes from a diverse crowd.
So it's a clever way to isolate and purify those desired compounds. And once we've purified it, we can just remove that tag and get our aldehyde back.
Exactly. It's a reversible reaction, so we can regenerate the aldehyde very easily by treating it with an acid or a base, like removing the costume after the dance is over.
That's so useful.
Yeah.
But what about other dance partners? I know Grignard reagents are key players in organic chemistry. Do they get to dance with aldehydes and ketones too?
They're always ready to join the party. Grignard reagents are powerful nucleophiles that can add to the carbonyl compounds and form alcohols.
Yeah.
They're like skilled builders. They can add those new carbon bonds, and they can create those more complex molecules.
Ah, those Grignard reagents. Always ready to lend a helping hand, or should we say carbon group, to create those bigger and better molecules. I remember learning about those reactions with aldehydes and ketones in organic chemistry. It's amazing how we can use them to create those carbon skeletons.
Exactly. And there are countless other nucleophilic addition reactions to explore. We can add alcohols to form hemiastols and acetols, react them with ammonia derivatives to form imines, oximes, and hydrozones, and even use some specialized reagents to tell the difference between aldehydes and ketones.
Wow. So many possibilities. It's like a never-ending dance party with all these endless combinations of partners and moves. It's amazing to see how these carbonyl compounds can transform and evolve through these nucleophilic addition reactions.
And we've just dipped our toes in the water. There's a whole ocean of reactions to discover. Each reaction will reveal new insights into this intricate world of carbonyl compounds. We can reduce them, oxidize them, explore the reactivity of those alpha hydrogens, and even delve into that fascinating world of carboxylic acids. Now that we've seen how nucleophiles can add themselves to aldehydes and ketones, let's explore another fascinating aspect of their reactivity: reduction.
So we're going from adding things to taking things away. Is it like slimming down those molecular structures?
It is a bit like that. In reduction reactions, we're essentially decreasing the number of carbon-oxygen bonds or increasing the number of carbon-hydrogen bonds.
So less oxygen, more hydrogen. Sounds like a molecular makeover. But how do we actually achieve this transformation? What kind of tools do chemists use for these molecular slimming procedures?
One common technique is called catalytic hydrogenation. We use hydrogen gas and a metal catalyst like palladium or platinum. And that adds hydrogen atoms across that carbonyl double bond. Think of it like a molecular seamstress, stitching in those hydrogen atoms to create a smoother, more saturated structure.
So we're breaking that double bond and adding two hydrogens, one to the carbon, one to the oxygen. It's like giving the molecule a hydrogen hug. But what if we want to go beyond just adding hydrogen? Are there other ways to reduce aldehydes and ketones? I've heard whispers about these powerful metal hydrides.
You've got a keen ear. Reducing agents like sodium borohydride, that's NaBH4, and lithium aluminum hydride, LiLH4, are like specialized delivery services. They can deliver hydride ions, which are negatively charged hydrogen atoms, directly to that carbonyl group.
So these hydride ions are like tiny little hydrogen packages ready to be delivered to that eager carbonyl group, and they act as nucleophiles, attacking that partially positive carbon. Right.
Exactly. And just like with the catalytic hydrogenation, we end up forming alcohols. Sodium borohydride is a bit more gentle, like a standard delivery truck, while lithium aluminum hydride is more powerful, like a high-speed courier. It can reduce not just aldehydes and ketones, but also carboxylic acids, esters, and amides.
It's like having a whole fleet of molecular delivery vehicles at our disposal, each with its own strengths and specialties. But let's push the boundaries even further. Can we take reduction to the extreme and reduce aldehydes and ketones all the way down to hydrocarbons? Can we completely eliminate that oxygen atom?
We can. There are two classic techniques, the Clemmensen reduction and the Wolff-Kishner reduction. Both of them are like molecular demolition experts. They're capable of transforming that carbonyl group into what we call a methylene group, CH2, so essentially replacing the oxygen atom with two hydrogen atoms.
Wow, so we're going from a carbonyl compound with that double bond to oxygen all the way down to a simple hydrocarbon with just carbon and hydrogen. That's a pretty dramatic transformation, like stripping a building down to its foundation. But what's the difference between those two methods? Do they have different demolition styles?
The Clemmensen reduction is like a heavy-duty wrecking ball. It uses zinc amalgam and concentrated hydrochloric acid. It's effective, but it's only suitable for molecules that can withstand those harsh acidic conditions.
Sounds intense. And what about the Wolff-Kishner reduction?
The Wolff-Kishner reduction is a bit more refined, like a precision demolition team.
Okay.
It uses hydrazine, NH2, and a strong base like potassium hydroxide in a high boiling solvent. It's the preferred method for molecules that are a little more sensitive to acids.
So depending on the molecule's fragility, we choose the appropriate method to remove that oxygen atom and create that hydrocarbon. It's like choosing the right demolition crew for the job. But now, let's shift gears from reduction and explore the opposite process, oxidation. If reduction is all about removing oxygen, is oxidation all about adding it back?
You've got the concept. Oxidation is the yin to reduction's yang. It involves increasing the number of carbon-oxygen bonds or decreasing the number of carbon-hydrogen bonds.
Okay, so we're either adding oxygen or removing hydrogen, or maybe even both. It's like reversing those molecular makeovers we talked about earlier. But how do we actually oxidize aldehydes and ketones? Do we have special oxidizing agents for this task?
Aldehydes are like eager participants in oxidation reactions. They readily transform into carboxylic acids, which have a carboxyl group, COOH, using common oxidizing agents like potassium permanganate, KMNO4, or potassium dichromate, K2CR207.
So it's like we're adding a crown to that aldehyde, transforming it into a carboxylic acid, the king of the carbonyl compounds. But what about ketones? Are they as eager to participate in these oxidation coronations?
Ketones are a little bit more reluctant to give up their throne. They need stronger oxidizing agents and harsher conditions to actually break that carbon bond next to the carbonyl group. It's like trying to dethrone a very stubborn ruler. You need a more forceful approach. This cleavage reaction results in a mixture of carboxylic acids, but they have fewer carbon atoms than the original ketone.
So it's not a simple coronation. We're breaking apart the ketone and oxidizing the fragments. But I'm curious, are there any tests we can use to distinguish between aldehydes and ketones based on their willingness to be oxidized?
You're thinking like a true chemist. There are indeed two classic tests, the Tollens test and the Feelings test, and they exploit this difference in reactivity.
Okay, so these tests are like molecular lie detectors. They reveal the true identity of our carbonyl compounds. Tell me more about the Tollens test. How does it work?
The Tollens test is like a magic mirror. It reveals the presence of an aldehyde. It uses a solution of silver nitrate, AgNO3, and ammonia, NH3, which forms a complex ion called the diamine silver ion, that's AgNH3 plus Li. When an aldehyde is added to this solution, it acts as a reducing agent. It donates electrons to the silver ions, and it transforms them into metallic silver, forming a shiny silver mirror on the inside of the test tube.
Wow, that's a pretty dramatic visual confirmation. And what about the feelings test? Does it involve some kind of magical transformation too?
The Feelings test relies on a color change rather than a mirror. It uses a solution that contains copper ions. Those are complex with tartrate ions. And when an aldehyde is added and then heated, it reduces those blue copper ions to a reddish-brown copper oxide, which forms a visible precipitate.
So we have these two elegant tests that really rely on the aldehyde's willingness to be oxidized. But I imagine there's some caveats, some exceptions that we need to be aware of. Not all aldehydes and ketones will behave in exactly the same way, right?
You're right. It's like any rule, there are always exceptions. For example, aromatic aldehydes, the ones with the benzene ring attached, they don't react with Feelings reagent. And certain ketones, like the ones with an alpha hydroxy group, can actually give false positive results with these tests. So we always need to consider the entire molecular structure in the context.
Got it. It's like being a molecular detective. We gather clues from different tests and we use our knowledge to piece together the true identity of that compound. But let's move on to a very specific type of oxidation reaction that's particularly useful for methyl ketones, the haloform reaction.
The haloform reaction is like a molecular sculptor. It selectively carves away a methyl group from a methyl ketone and replaces it with 3 halogen atoms. So that's chlorine, bromine, or iodine. And this transformation creates a haloform like chloroform, CHCl3, or bromoform, CHBr3.
So we're taking a methyl ketone and swapping out that methyl group for 3 halogen atoms, and we create a haloform. What happens to the rest of that ketone molecule during this molecular sculpting process?
The remaining part of the ketone molecule actually undergoes oxidation, and that transforms it into a carboxylic acid with 1 fewer carbon atom than the original ketone.
So it's like we're cleaving the ketone at that specific point, and we're oxidizing both of the fragments. But what makes this reaction so specific to methyl ketones? Why don't other ketones undergo this haloform transformation?
The key is that unique reactivity of those alpha hydrogens. So those are the hydrogen atoms that are on the carbon next to the carbonyl group. In methyl ketones, those alpha hydrogens are more acidic because when you remove one, it creates an enolate ion that's stabilized by resonance.
Ah, resonance again. It seems like this electron delocalization is always playing a key role in organic chemistry, stabilizing reactive species, influencing reaction pathways. So it's the acidity of those alpha hydrogens that allows this haloform transformation to occur. But is this reaction just a fascinating chemical phenomenon, or does it have any practical applications?
The haloform reaction has a fascinating history. It was actually used to produce chloroform, bromoform, and iodoform, which were once very widely used as anesthetics and antiseptics. Nowadays, it's still used in organic synthesis and as a qualitative test for methyl ketones.
Incredible how a seemingly simple reaction can have such a rich history and diverse applications. But now, let's dive deeper into those versatile alpha hydrogens and explore the reactions that make them so special.
The acidity of those alpha hydrogens is a key concept to understanding the reactivity of these carbonyl compounds. It's the driving force behind some reactions like aldol condensation and the Cannizzaro reaction.
Okay, so those alpha hydrogens are like little molecular handles. They allow us to grab onto the molecule and perform all sorts of interesting transformations. Let's start with aldol condensation. What's happening in this molecular dance?
Aldol condensation is a beautiful reaction. An enolate ion, which is formed by removing a proton from the alpha hydrogen, acts as a nucleophile. And that attacks the carbonyl group of another aldehyde or ketone. This creates a beta-hydroxyaldehyde or a beta-hydroxyketone. It's a molecule that's affectionately known as an aldol.
So it's like a molecular tango, with one aldehyde or ketone molecule gracefully reaching out to another. And they're joining together, forming a new carbon-carbon bond and creating this aldol product. But those names, aldol, beta-hydroxyaldehyde, beta-hydroxyketone, can we break those down a bit? They're kind of a mouthful.
Of course. Aldol is just a clever blend of aldehyde and alcohol, representing the two functional groups that are present in the initial product. Beta-hydroxy simply indicates that the hydroxyl group is located on the beta carbon, which is 2 carbons away from the carbonyl group. So a beta-hydroxyaldehyde has an aldehyde and a hydroxyl group 2 carbons apart. And a beta-hydroxyketone has a ketone and a hydroxyl group 2 carbons apart.
So it's all about location, location, location. The names are just describing the functional groups and their addresses on the molecular map. But what happens to that aldol product is at the end of the dance?
Often, that aldol product undergoes a little slimming down. It loses a water molecule in a process called dehydration, forming an alpha, beta-unsaturated aldehyde, or ketone. And that new molecule has a conjugated system, so a system of alternating single and double bonds that extend that electron dance, and that makes it more stable.
So we're removing water, creating a double bond, and extending that electron party, making the molecule more stable in content. But I know there's more to the aldol condensation story. What about cross-aldol condensation? Does that involve a more diverse set of dance partners?
Cross-aldol condensation is like a molecular mixer. It brings together 2 different aldehydes or ketones. It's a little bit more unpredictable, though, and it can lead to a mixture of products depending on which molecules actually decide to act as nucleophiles and which ones decide to act as electrophiles.
So it's like a molecular matchmaking service, but with a little bit more chaos. We mix different aldehydes and ketones and see who pairs up. But that sounds like it could get messy with all those potential combinations. How do chemists manage to control this reaction and guide it toward the desired outcome?
Chemists have a few tricks up their sleeves. One strategy is to use a reactant that actually lacks those alpha hydrogens, and that ensures that it can only act as an electrophile. So it's like a wallflower waiting to be asked to dance.
Right.
Another approach is to very carefully fine-tune those reaction conditions, things like temperature and base concentration, to favor the formation of specific pairings.
It's like setting the stage for a successful molecular romance, choosing the compatible partners, and creating the perfect ambiance for their interactions. But let's shift our focus to another intriguing reaction, the Cannizzaro reaction. How does this dance differ from the aldol condensation?
The Cannizzaro reaction is a very unique performance. It's reserved for aldehydes that lack those reactive alpha hydrogens. It's like a self-sufficient dance, where one aldehyde molecule acts as both an oxidizing agent and a reducing agent. It transforms itself into a carboxylic acid and an alcohol.
Wait, so the same molecule is both oxidized and reduced. It's like a molecular Jekyll and Hyde. How is that possible?
It's called a disproportionation reaction, and it happens because the aldehyde can actually play both roles, electron donor and electron acceptor. In the presence of a strong base, like hydroxide ions, one aldehyde molecule very generously donates a hydride ion, that's H, to another, and that oxidizes itself in the process and reduces its partner.
So it's like a molecular tug-of-war. One aldehyde wins, claims that electron, and becomes a carboxylic acid. The other loses, gains an electron, and becomes an alcohol. But why is this unique dance restricted to aldehydes without those alpha hydrogens? What makes them so special?
Aldehydes without alpha hydrogens can't form those reactive enolate ions, which are the key players in that aldol condensation. So when they're faced with a strong base, they opt for this self-sufficient Cannizzaro reaction instead. It's their unique way of dealing with the situation.
It's like they've adapted their dance moves to fit their specific molecular structure.
Yeah.
But now let's step back from those alpha hydrogens and revisit electrophilic aromatic substitution. We touched on this briefly with aldehydes and ketones, but I'm curious to know how the carbonyl group influences these reactions when it's part of an aromatic compound.
The carbonyl group, with its electron-withdrawing nature, exerts its influence even when it's attached to that aromatic ring. It pulls electron density away from the ring, and that makes it less reactive toward that electrophilic attack. It's like a protective parent shielding the ring from those eager electrophiles.
So it's making the ring less welcoming to those electron-seeking electrophiles. But does it have any preference for where they can attach?
Absolutely. The carbonyl group directs the incoming electrophile to what we call the meta position, 2 carbon atoms away from itself. It's like a strategic placement, ensuring that that electrophile attaches at that specific location.
So the carbonyl group is not just a protector, it's also a director, guiding those electrophiles to that designated spot. This is all so fascinating. We've explored so many different aspects of the chemistry of aldehydes and ketones, from their structure and reactivity to their unique transformations. It's incredible how much complexity arises from a seemingly simple functional group, like a carbonyl group. But we still have one more important class of carbonyl compounds to explore, the majestic carboxylic acids.
You're right. Carboxylic acids are like the crown jewels of the carbonyl world. They possess a very unique combination of properties. They're acidic, they can form a wide variety of derivatives, and they're just essential players in so many different biological processes. Get ready to enter the realm of carboxylic acids and discover their fascinating secrets.
I'm ready to be dazzled by these crown jewels of the carbonyl world. But first, let's start with the basics. What exactly defines a carboxylic acid? What makes them stand out from the aldehydes and ketones that we've been exploring?
Carboxylic acids are all about that carboxyl group. So that's that neutral COH, a powerful combo of a carbonyl group and a hydroxyl group, both attached to the same carbon atom.
So it's like a molecular power couple, blending the reactivity of the carbonyl group with the acidity of the hydroxyl group.
Exactly.
But how does this unique structure translate into real-world properties? Let's start with names. How do chemists label these intriguing molecules?
Just like with aldehydes and ketones, we've got both common names and those IUPAC names for carboxylic acids. The common names are often rooted in history or the origin, like take formic acid that was named after those industrious ants.
I always appreciate those historical tidbits. It really reminds us that chemistry is just woven into the fabric of our world. And what about the more systematic IUPAC names? Do they follow a similar pattern to the aldehydes and ketones?
They do. We start with the name of the corresponding alkane, and we replace that E with oic acid. For instance, acetic acid, the tangy component of vinegar, becomes ethanoic acid because it's got those 2 carbon atoms just like ethane.
So it's ethane plus oic acid, giving us ethanoic acid. Simple and elegant, but names are just the surface. Let's delve into the molecular architecture of the carboxyl group. What secrets does its structure hold?
Okay, so picture that carboxyl group. It's flat, it's planar, that carbon atom is right in the center, and it's forming a double bond with 1 oxygen and a single bond with the hydroxyl group. And the oxygen in that hydroxyl group, it even has those 2 lone pairs of electrons just ready to participate in some interesting interactions.
Okay, so we've got this flat, planar structure with both a double bond and a single bond to oxygen. How does this unique arrangement affect the carboxyl group's personality?
Well, that combination of a carbonyl group and the hydroxyl group makes the carboxyl group superpolar, and that creates those attractive forces between molecules, which influences properties like boiling point and solubility.
So those intermolecular forces are at play again, dictating how these molecules interact with each other. But I know carboxyl acids are really famous for their acidity. What makes them more willing to give up a proton than their alcohol cousins?
It all comes down to that resonance stabilization. When a carboxylic acid loses a proton, it forms what we call a carboxylate anion, where that negative charge can be shared between those 2 oxygen atoms through resonance. It's like those electrons are playing a game of molecular tag. They spread out that negative charge and make that anion more stable.
So the more stable the anion, the happier the acid is to lose its proton. Makes sense. But how do carboxylic acids stack up against other acids, like those strong mineral acids?
Carboxylic acids are generally weaker than mineral acids like hydrochloric acid or sulfuric acid. Mineral acids are like those eager beavers. They completely ionize in water and readily donate their protons. But carboxylic acids are a bit more reserved. They only partially ionize, which creates an equilibrium between the undissociated acid and that carboxylate anion.
So it's a matter of degree. Some acids are more eager to donate their protons than others, but carboxylic acids are still stronger than alcohols, which makes them an intriguing class of compounds. But now I'm curious about how we make these carboxylic acids in the first place. Do they require some special molecular alchemy?
Not quite alchemy, but we do have a variety of methods to synthesize them, and many of these techniques actually build upon those reactions that we've discussed for aldehydes and ketones. So for instance, we can oxidize primary alcohols and aldehydes to create carboxylic acids.
Yeah, right. We learned earlier that aldehydes can be easily oxidized using those common oxidizing agents like potassium permanganate and potassium dichromate. And primary alcohols can be first oxidized to aldehydes and then further oxidized to carboxylic acids. It's like a stepwise molecular transformation.
Exactly, and we can use those same oxidizing agents, we just have to tweak the conditions a bit to get that desired outcome. But there are other methods too. We can prepare carboxylic acids from alkylbenzenes, nitriles, imides, Grignard reagents, acyl halides and hydrides, and even esters. It's like having a molecular toolbox filled with different tools for building carboxylic acids.
So many possibilities. It's amazing to see how all these different starting materials can be transformed into carboxylic acids. It's like a molecular puzzle, figuring out the best way to assemble the pieces. But I'm getting a little lost in all these different starting materials. Can you give us a specific example? Like, how would we go from an aldebenzene to a carboxylic acid?
All right, imagine an alkylbenzene with its aromatic ring and an alkyl side chain attached. We can treat it with a strong oxidizing agent like potassium permanganate or chromic acid, which basically just cleaves off that side chain no matter how long or complex it is, and it replaces it with a carboxyl group.
Wow. So it's like molecular surgery, removing one part and replacing it with that carboxyl group. Pretty impressive.
And what about those nitriles with their carbon-nitrogen triple bonds? How do we transform them into carboxylic acids?
Nitriles are like molecular sponges. They're ready to soak up water molecules. And so we can hydrolyze them using either an acid or a base catalyst to break that triple bond. And we add those elements of water, which forms that carboxyl group.
So we're essentially adding water across that triple bond, creating a carboxylic acid. And what about those versatile Grignard reagents? Can we use those molecular builders to create carboxylic acids too?
Absolutely. Grignard reagents are like molecular architects. They're ready to construct new structures. If we react them with carbon dioxide, like dry ice, it creates a carboxylate salt, which we can then acidify to yield the carboxylic acid.
So we're capturing carbon dioxide from the air and using it to build a carboxylic acid. It's like a molecular recycling project.
And what about those acylic halides and hydrides? How do they fit into this molecular construction site?
Acyl halides and anhydrides are like prefabricated building blocks. They're ready to be assembled into those carboxylic acids, and we can hydrolyze them just by reacting them with water, and that breaks those specific bonds and adds in the elements of water to form the carboxyl group.
Got it. So whether we're breaking a bond to a halogen in an acyl halide or a bond between those two carboxylic acid units in an anhydride, we're basically adding water and creating a carboxylic acid. And what about those fragrant esters? Can we coax them into becoming carboxylic acids too?
Esters, those masters of fragrance, can also be transformed into carboxylic acids through hydrolysis. And again, we can use either acid or base catalysis. The acidic hydrolysis is like a gentle unzipping. It cleaves that ester bond and adds water to form the carboxylic acid and an alcohol. And basic hydrolysis, which is often called saponification, that's a little bit more forceful, that forms a carboxylate salt, which we can then acidify to yield that carboxylic acid.
It's amazing how many different pathways lead to carboxylic acids. It's like a molecular choose-your-own-adventure story. But let's take a break from synthesis and explore the physical properties of carboxylic acids. What can we learn about them just by looking at them, smelling them, or even tasting them?
Just like with aldehydes and ketones, the physical properties of carboxylic acids are connected to their molecular structures and the forces that exist between those molecules. So those intermolecular forces like hydrogen bonding and dipole interactions, they play a crucial role in determining properties like boiling point, solubility, and even their odor.
Okay, let's unpack those intermolecular forces. How do they affect the boiling points of carboxylic acids? How do they compare to other organic compounds?
Carboxylic acids are the champions of hydrogen bonding. They can form strong hydrogen bonds not only with water molecules, but also with each other. They create these dimers, pairs of molecules linked by two hydrogen bonds. And this makes them a lot more difficult to separate, leading to higher boiling points compared to hydrocarbons, alcohols, and even aldehydes of similar size.
So it's like those carboxylic acids molecules are holding hands, clinging tightly to each other and resisting the urge to boil away. But what about solubility? How do carboxylic acids interact with water?
The solubility of carboxylic acids in water depends on a familiar struggle, the battle between the hydrophilic and the hydrophobic. Smaller carboxylic acids, like formic acid and acetic acid, those are water-soluble superstars.
Right.
They readily form hydrogen bonds with water molecules and dissolve completely.
So those smaller carboxylic acids are eager to join that water party. But what about their larger counterparts with those bulky hydrocarbon chains? Do they shy away from those water molecules?
As those hydrophobic hydrocarbon chains grow larger, they start to dominate the molecule's personality. These larger carboxylic acids become less soluble, or even insoluble in water, because those hydrophobic chains disrupt that hydrogen bonding network of water molecules.
It's that classic tug of war between the water-loving carboxyl group and those water-fearing hydrocarbon chains. But how does this interplay between structure and solubility affect their odor? Do those hydrophobic chains mask the scent of that carboxyl group?
They do. Smaller carboxylic acids, like formic acid and acetic acid, have those sharp, pungent odors, like a really strong vinegar smell. But as the size of the molecule increases, that odor becomes less intense and can even take on a pleasant, fruity aroma, like the scent of some esters.
So it's like we're adding a fragrant mask to that pungent carboxyl group. But speaking of sensory experiences, what about taste? Do carboxylic acids contribute to our culinary adventures?
Absolutely, they're the masters of tartness. Carboxylic acids are responsible for that sour taste of so many foods, like the citric acid in lemons and limes, or the lactic acid in yogurt and sourdough bread.
Amazing how these carboxylic acids can add such a vibrant dimension to our taste buds. But I know there's more to their story. They're not just about taste and smell. They're also incredibly reactive. Let's explore the world of their chemical reactions.
Carboxylic acids are indeed versatile players in the world of chemistry. Their reactions can involve breaking the OH bond, breaking the COH bond, substituting something else for those hydrogens in the hydrocarbon part, and even transforming the carboxyl group itself.
Wow, so many possibilities. It's like they're molecular multitaskers, capable of undergoing a whole range of transformations. But let's take it one step at a time. What kind of reactions involve breaking the OH bond? What's happening at the molecular level?
One of the most important reactions involving that OH bond cleavage is esterification, where a carboxylic acid reacts with an alcohol to form an ester, and that releases a water molecule in the process. This reaction is catalyzed by acid, and it involves a very graceful molecular dance. It's called nucleophilic acyl substitution, where the alcohol acts as a nucleophile and attacks that carbonyl group of the carboxylic acid.
Ah, esterification. It's the reaction that gives us those delightful, fruity-smelling esters. But can we refresh our memories on the steps involved? How does this molecular dance actually work?
Picture the carboxylic acid with its carbonyl group and its hydroxyl group. That acid catalyst protonates that carbonyl oxygen, which makes that carbon even more attractive to those nucleophiles. And the alcohol, eager to join the dance, attacks that carbonyl carbon, which forms that tetrahedral intermediate.
So the alcohol is drawn to that partially positive carbon, and the double bond opens up to accommodate it. What happens next in this intricate molecular choreography?
A proton transfer within that intermediate converts that hydroxyl group into a good leaving group. It's like a quick costume change, preparing it to exit the stage. And then, like a perfectly timed finale, that leaving group departs, taking a water molecule with it and leaving behind the ester.
It's a beautiful sequence of steps, with each player performing its role to perfection. But esterification isn't the only reaction involving that OH bond cleavage, right? What other transformations can carboxylic acids undergo?
We can also create anhydrides by dehydrating carboxylic acids, essentially removing water from two molecules and linking them together through an oxygen atom. It's like a molecular matchmaking service, bringing two carboxylic acids together to form a new bonded pair.
So it's like we're stitching two carboxylic acid molecules together, removing a water molecule as we so. Pretty straightforward. But what about reactions involving the COH bond cleavage? What kind of molecular makeovers can we achieve by breaking that bond?
One really powerful transformation involving that COH bond cleavage is reduction. So where we convert a carboxylic acid to a primary alcohol, and we need to call upon those powerful reducing agents like lithium aluminum hydride, LiOH4, or diborane, B2H6 to actually accomplish this task.
Those familiar reducing agents. We've seen them in action before, transforming aldehydes and ketones into alcohols. But is there anything special we need to consider when we're reducing carboxylic acids? Are they more resistant to this transformation?
Yes, carboxylic acids are a bit more stubborn than aldehydes and ketones when it comes to reduction. That COH bond is a bit tougher to break, We need those stronger reducing agents and more persuasive reaction conditions.
So it's like we need to convince those carboxylic acids to let go of their oxygen. But once we've successfully reduced them, we end up with a primary alcohol, just like with the aldehydes and ketones. Pretty neat. But I know there's another intriguing reaction involving COH bond cleavage, decarboxylation. What's happening in this dramatic transformation?
Decarboxylation is like a molecular weight loss program. We remove carbon dioxide, CO2, from the carboxylic acid, and that leaves behind a slimmed-down hydrocarbon. It's like taking a balloon and letting the air escape, and you're just left with a deflated piece of rubber. This reaction usually requires high temperatures, and it often involves a base or a metal catalyst to help things along.
So we're essentially removing that entire carboxyl group and releasing carbon dioxide into the atmosphere. But what makes this reaction possible? Why would a carboxylic acid willingly give up its identity?
It all comes down to stability. The driving force behind decarboxylation is actually the stability of the carbanion that forms after that carboxyl group departs. If that carbanion is stabilized by resonance or electron withdrawing groups, the carboxylic acid is more willing to let go and release that carbon dioxide.
Stability again. Seems like stability is the ultimate goal in the molecular world. But let's move on to those substitution reactions in the hydrocarbon part of carboxylic acids. What's happening in these molecular makeovers?
Substitution reactions in that hydrocarbon part involve replacing a hydrogen atom on the alkyl or aryl group with another atom or group. One classic example is the Helmholtz-Zielinski reaction, where we target those reactive alpha hydrogens again and replace one of them with a halogen atom, like bromine or chlorine.
So we're back to those versatile alpha hydrogens. They always seem to be at the heart of the action. But how does this Helmholtz-Zielinski reaction actually work? What's the molecular choreography behind this halogenation?
It's a multi-step process, like a carefully choreographed dance routine. So first, we activate the carboxylic acid. We convert it into an acylhalide using a phosphorus halide, like phosphorus tribromide, PBr3. This makes it much more receptive to the halogen, which then attacks that alpha carbon, and that forms an alpha haloacyl halide. Finally, we hydrolyze that intermediate, replace that halogen on the carbonyl group with a hydroxyl group, and we've created an alpha halocarboxylic acid.
So it's a carefully orchestrated sequence of steps: activation, halogenation, and then hydrolysis to achieve the desired outcome. Pretty impressive. But what about other substitution reactions? Can we add other groups to that hydrocarbon part beyond just halogens?
We can also do ring substitutions on those aromatic carboxylic acids, like benzoic acid. However, remember that carboxyl group is a bit of an electron hog. It deactivates the ring and makes it less reactive toward electrophilic attack, and it directs the incoming electrophile to that meta position.
That familiar meta-directing influence of that carbonyl group. It seems like whether it's part of an aldehyde, a ketone, or a carboxylic acid, that carbonyl group exerts its control over that aromatic ring. But now let's shift our focus to the final frontier of carboxylic acid reactions. Reactions that actually transform that carboxyl group itself.
Reactions involving that carboxyl group often involve creating derivatives like esters, amides, and acid chlorides. These derivatives are incredibly useful. They can protect the carboxyl group during other reactions. They can activate that carboxylic acid for further transformations or even introduce new functional groups into the molecule.
So it's like we're giving that carboxyl group a makeover, transforming it into something new and exciting. But can you give us some specific examples? How do we create these derivatives and what are their unique talents?
Well, we've already encountered one of the most famous derivative-forming reactions, esterification. Remember that beautiful molecular dance between a carboxylic acid and an alcohol, catalyzed by acid? It's the reaction that produces those delightful esters, responsible for the scents of fruits and flowers, and used in countless applications, from solvents to perfumes.
Those versatile esters. They truly add fragrance and flavor to our world. But what about amines? How do we create those and what roles do they play?
Amides are formed by reacting a carboxylic acid with ammonia or an amine, and they're essential for life itself. They're the building blocks of proteins, and they're also used in a wide variety of industrial applications, from polymers to pharmaceuticals.
So amines are the workhorses of the molecular world, both in nature and in industry. And what about those reactive acid chlorides? How do we create those and what makes them so special?
Acid chlorides are formed by reacting a carboxylic acid with phenyl chloride, SOCl2, or phosphorus pentachloride, PCl5. They're very reactive. They're eager to share that acyl group with other molecules. And chemists often use them as intermediates in organic synthesis, like molecular couriers delivering that acyl group to create new complex structures.
So they're like the special forces of the carbonyl world, ready to react and transform other molecules. But now let's wrap up our exploration of carboxylic acids by talking about their real-world applications. We know they're responsible for the tangy taste of many foods, but what other roles do they play in our world?
Carboxylic acids are ubiquitous. They're used as starting materials for creating other chemicals, like those esters, amides, and acid chlorides that we just talked about. They're essential in the production of polymers, pharmaceuticals, detergents, and they even play really important roles in the food industry as preservatives and flavoring agents.
It's amazing to see how these seemingly simple molecules have such a profound impact on our world. From the flavors in our food to the materials we use every day, carboxylic acids are truly essential players. And we've only just scratched the surface of their fascinating chemistry.
What's truly remarkable is how much we've covered in this deep dive. From the simple structure of that carbonyl group to the complex reactivity of carboxylic acids, it's really a testament to the beauty and the complexity of organic chemistry.
We've explored their names, their structures, their reactions, their applications. It's incredible to see how much information is packed into these tiny little molecules.
And the journey doesn't stop here. Now that you have this really solid foundation, I encourage you to keep exploring. Delve deeper into specific areas that pique your interest. The world of organic chemistry is vast and full of wonder, waiting to be discovered.
Exactly, and who knows, maybe one day you'll be the one making groundbreaking discoveries in the world of carbonyl compounds.